किसने सर?
स्पीकर में।
Just let me know, sir. I just confirm, sir.
हाँ, डॉक्टर मुकेश जेवरिया। हेलो सर।
I mean,
ओह ग्रेट, ग्रेट टू सी यू।
great to see you, sir. Great to see you. Thank
थैंक
you.
यू वेरी मच सर।
Thank you very
थैंक यू वेरी
much.
मच। या इन माय एरिया द पावर इज नॉट
Okay,
available
okay,
right now,
okay, no
so
problem.
I'm little bit sitting outside. So how are you?
I'm good, sir. I'm good. Thanks for your invitation.
Yeah, it's great to see you. A long
Good
time.
to see you. It will be a good interacting talk.
Yes sir, yes sir. Let us wait for another.
Yeah, yeah, I am waiting. Don't worry. Just
Okay,
let me
fine.
know when to start.
Okay, okay.
ये वाले से करेक्टाइजेशन तो करवा ले अभी, है ना?
Hello, Mane.
Yes, sir.
Mane.
Yes, sir.
Hello.
Hello. Yes, sir. Am I audible?
Voice is low. Maybe it is
हेलो सर आपकी
not
आवाज क्लियरली नहीं आ रही है.
okay.
हाँ
Okay.
सर, हाँ मेरे को आ रही है आवाज।
Manya,
आपकी
you are
सब
audible.
मेरे
Start.
को आपकी सबकी आवाज आ रही है।
Sir, I should I start?
Hello. Hello, buddy.
Yes, sir.
You can start now.
Okay, sir. Good morning to all dignitaries, the guests, and students. I am Manya. It gives me immense pleasure to extend you a very warm welcome on behalf of the Department of Physics, Ramjas College, clubbing us all for a lecture on a very crucial subject matter. Organizing this lecture exclusively for the students of our physics, of our institution of education. With profuse elation, I would like to introduce our guest, Dr. Mukesh Jewariya, Senior Scientist and Assistant Professor at Academy of Scientific and Innovative Research, working at the National Physics Laboratory in the Council of Scientific and Industrial Research, who will share his invaluable knowledge in today's lecture, Terahertz three-dimensional imaging, an approach for safe society. Now, I would like to introduce our principal, Professor Manoj Khanna, under whose guidance our college keeps growing its academic and artistic glory. May I ask him to share some words of wisdom with us?
Hello. Principal sir has joined or not? I don't think sir has joined. Hello. Manya.
So, I don't know whether he's mind.
Okay, no problem. No problem. You can go ahead now.
Okay. Now I welcome the head of department, Professor Ashok Kumar, IQAC advisor, Professor Hemant Kumar Rajor, staff advisor, Dr. Jagjeevan Ram, and faculty members whose dedication makes it possible for all of us to get the best quality of education and support. To all the students, what else can I say? But you are about to experience one of the most fascinating seminars that you have ever have and ever would. Now I would invite the staff advisor and an esteemed member of the faculty, Dr. Jagjeevan Ram, to progress today's seminar.
Thank you, Manya. Let us introduce our esteemed guest. Dr. Mukesh Jewariya received his MSc in Physics in 2003 from Indian Institute of Technology, Roorkee. Uh, am I audible?
Yes, sir.
Okay, fine. Uh, and MTech in Laser Technology in 2006 from Devihalya Viswavidyalaya, Indore. He received his DSc in Physics from Quito University in 2010. From 2010 to 2011, he worked as a specially appointed researcher in the Innovation Center for Instrumentation for Science, Education and Technology, Osaka University. Later, he also worked, and later on from 2011 to 12, in between that, he worked as an assistant professor in the Institute of Technology and Science, the University of Tohoku, Japan. He was a visiting scientist from 2015 to 2017 at Korea Atomic Energy Research Institute, Daejeon, South Korea. Currently, he is working as a senior scientist at CSIR uh, NPL mean the National Physical Laboratory, New Delhi, from 2012. He is a recipient of Mokuso Fellowship Japan 2006, JCPS Kakeni 2011, Korean Research Fellowship 2015 to 2017, and Then he is also qualified the most examination that like a GATE, CSAR, NET, JEST, etc. Here. Uh, he's also guiding PhD students, and he has more than 53 publications and two book chapters, and more than 60 conference papers in international and national conferences as well as in journals. He is a life member of Indian Session of Physics, Indian Physics Associations, Indian Laser Association, Optical Society of America, Optical Society of India, uh, Japanese Physical Society, Korean Physical Society, etc. He is an editorial board of Optical Material, Optical Communication, and other journals. He is a reviewer of many journals, including PRL, PRB, IEEE, JOSA A, JOSA Optical Letters, Material, Express, etc. His research interest includes generation of high-power terahertz pulse, terahertz spectroscopy, terahertz imaging, and terahertz frequency meteorology, length meteorology, dimensional meteorology, development of material for terahertz detectors, and ultra-fast spectroscopy. Uh, Currently, he is working to realize the SI unit of meters using quantum standard optical frequency combo. We welcome you, sir, on the behalf of Physics Department of the Ramjas College, and I invite you to deliver a talk.
Thank you, Dr. Jagjeevan, and thanks to your college principal and all the members who are in this arrangement of this talk. And I really thanks for my introduction. And today, for the students, I will introduce a new technique, and that is terahertz. And terahertz is a very recent and fast growing field now, which is now in a process to replace the old imaging technique like X-ray, ultrasonic, because X-ray is invasive. It creates a harmful effect on our body when it passes through the body, when we go at the airport, medical diagnostic. And ultrasonic is a contact method. So we want a non-contact method to see like inside. Many women sometimes hesitate to take the ultrasonic image. So similarly, the world now want a non-invasive and non-contact technique. So with this approach, I will go and I will share you my recent results. I think you are able to see my slides. Okay, just tell me, are you able to
Yes,
see my
yes,
slide?
yes, Manoj.
Okay, so as
Yes, yes, Mukesh, yeah.
okay, so my the title, as you know, I gave there terahertz imaging as approach for safe society. So terahertz computed tomography means computed tomography means we reconstruct the image of something we capture. That is computed tomography using some computer algorithm or programming. So based on the X-ray tomography, we are in a process now to develop terahertz tomography. If you see, these are the terahertz image. These images mostly captured by my group, and here in this. So in later slide, I will tell you what kind of image we get. But before that, let me introduce what is terahertz. You know X-ray. Everybody knows X-ray. Okay, so this is X-ray here. You see, this X-ray is used for imaging. So imaging of biomedical imaging, okay, in your body parts, imaging of baggage at the airport, and imaging of the crystals, okay, crystallography. Okay, so the X-ray is used, but as we know, X-ray is an invasive technique in which a harmful effect can be created in the body. It will lead to the change in our genome structure, which leads to gives some kind of disease. It's harmful to our body. So if you see here, it's terahertz. Terahertz is the sandwich region between microwave, means electronics, and photonics, infrared. Okay, this particular frequency region is also very rich in science, where means all the most fundamental phenomena take place in picosecond regime. In so this not only for rich in science, but it gives very good imaging. So you see, biomedical imaging can be done by this. Screening can be done. So there are two big technique for imaging: a terahertz or X-ray. Okay, so terahertz is what? A terahertz is a bridge between electronics and photonics. So 1 terahertz is equal to 10 to the power 12 hertz. That's a frequency. But when we go in time, it's 1 picosecond, 10 to the power minus 12 second. And this is around 300 micrometer. So the property of imaging came from this factor, that is 300 micrometer. It means it can easily pass through the cardboard, wood, plastic, paper, soft material other than the hard material. So at the airport, at the other places, security, VIP security, something is either hidden in paper, cardboard, plastic, or cloth in the, that's why. So that's why terahertz is coming into the picture to do imaging. Okay, so terahertz is a bridge between electronics and photonics. So as my from my talk, what I want to introduce, terahertz imaging. Now you know terahertz. What is terahertz? Now what is imaging? We know image, our shadow is also a image. So if we shine any radiation of any kind, whether it's X-ray, whether it's infrared, whether it's terahertz, anything, if a radiation of any kind emitted from और अफेक्टेड बाय एन ऑब्जेक्ट, है ना, जो हम लेंस से बनाते हैं, सबको इंग्लिश समझ में आएगी मेरे ख्याल से, है ना. सो इसक्यूज ए रिप्रेजेंटेशन, एंड दैट रिप्रेजेंटेशन इज image. So whatever, by transmitting the light, reflecting the light, or emitting the light, if there are kind of some representations in close, that representation is an image, that image of a object, some aspect of the object generated, or then the systematized body of the knowledge relating to the generation properties and processing of the representation may be defined as imaging. So image is just a representation, but the systematized body of the knowledge, that is known as imaging. Imaging means some, you will see some kind of pattern, some kind of systematic behavior. So terahertz is doing, as I said, many other things. So it can do the non-destructive testing by imaging. You see, we can see the building cracks. We can see the cracks in electronic part. We can do the imaging of dangerous weapon, explosive at the airport. You see, now this is terahertz scanner, and your baggage is going from here. Are you able to see my cursor? Okay, so we can check these kind of things using terahertz. You can check, you can do imaging of what is inside your packed item. You ask the material from Amazon, Flipkart. If somebody give a box, what is inside that box? Okay, then similarly for medical, you can see the imaging of tumor, breast tumor, cancerous cell, non-cancerous cell. So terahertz is a very good tool nowadays to do imaging of from biomedical. So I will say now from biomedical to astro. Okay, you can do imaging in the space, because space is black body radiation, and terahertz is also a black body radiation. So Hubble telescope, now a new telescope, all they are kept doing the terahertz imaging. So coming year could be the golden years for terahertz. So let's go imaging through the history. Means the first image, you know, daguerreotype. Daguerreotype is the scientist who made our picture film, जो हम फोटोग्राफी करते हैं ना, फोटोग्राफिक. So the photographic in 1839, daguerreotype, this person make the first image, and to do this first image he took more than 48 hours, continuous sitting 48 hours. Okay, so imaging in the history first time did by this daguerreotype, and that image is the first photograph of the world in 1839. Then after 4 decades, in 1895, people used X-ray for imaging. And see, this is the X-ray image of Rontejan's wife. Rontejan just got engaged, and this is the engagement ring of his wife, and this is the hand of his wife. So then another imaging after 4 decades came as a X-ray image. But after just 1 century, you see, from 1895 to 1995, the first terahertz image of this is the chip, electronic chip inside a computer. So the first image other than this was captured by far infrared also. They did the imaging of a key. Then key imaging was like this one. So they use commercial HCN, hydrogen cyanide laser. But after this imaging, they stopped this one because there are two things. One is cyanide is poisonous. So doing the experiment with cyanide laser is very, very dangerous. So people rule out this technique. Then second thing is the detector needed to get the image is based on cryogenics, liquid helium. So doing the experiment with liquid helium is very, very risky and challenging. So in 1976, before terahertz, people started for infrared imaging, but that time people don't know that is terahertz. So terahertz is nothing but a far infrared radiation. So this was rapidly grow, and people captured the attention that if we use any far infrared radiation, then we can do better imaging. So then the first terahertz image, as I show you in 1995 by Hu and Nas, and they did the imaging of a IC chip and the plant leaf. You see here. So what they use? They use a terahertz emitter, antenna, transmitter, put the sample here, do the raster scanning, and on terahertz detector, they capture the image. So this was the image. But you know why terahertz imaging is required? Huh? Why there is a photograph we can see, and there is a X-ray image already doing everything. But why we need? Because most of the material in this universe, around 99% of the material on this earth or universe, have fingerprint spectrum between 0.1 to 10 terahertz. So to know the basic fundamental properties, basic fundamental imaging, terahertz imaging is required. Terahertz radiation strongly interact with material because the order of their wavelength corresponds to that of a molecular level structure. So terahertz is of rotational energy level, same as our lowest energy spectrum rotational. So that's why they can easily have a resonance. Terahertz frequency is accommodate all the semiconductor, but the most important is terahertz. Why? Because in conventional X-ray, ultrasonic, infrared, and millimeter wave, there are some kind of problem. Like X-ray have invensive effect, ultrasound have contact effect, infrared have poisonous effect, millimeter cannot easily pass. So terahertz comes into the picture. One thing. Second thing, it does not ionize the material. Terahertz X-ray can get ionized. X-ray ionize the material. So when it's ionized, you will not capture the basic information. So terahertz is a non-contact, non-invasive technique, and it's have other technique have only the amplitude phase part we cannot detect in other technique infrared and X-ray, but in terahertz we can detect the phase part. So when we detect the phase part, we can do 3D, 4D imaging and color image. So X-ray give monochromic image. If you see always X-ray as a two-dimensional monochrome image, but terahertz is three-dimensional. I will tell you the four-dimension also, and the three-dimension after that it gives the color image. So there are two kinds of technique doing the terahertz imaging. One is continuous terahertz imaging, one is pulse terahertz imaging. So I will just give you example what do you mean by continuous and pulse and where it is used. Suppose something is there in this room. Okay, let's say suppose a bomb is kept at a station, metro, airport, somewhere. Okay, a bomb is kept to treat. So where is the bomb? To locate the things, continuous terahertz imaging is required. But what kind of bomb it is? It is TNT, RDX, CNT. Then we need the pulse. So in pulse we have phase. Phase information give us the chemical composition. So this is the main reason why terahertz imaging is nowadays important as compared to X-ray, because in X-ray scanner if you see a talcum powder and RDX, it looks you the same as a talcum powder both, unless until you open it, check on another technique, then only you can distinguish. But terahertz can distinguish. So this is a typical terahertz system where you have transmitter TX and then a receiver RX. A beam is passing through here and a sample is put here. So this is continuous pulse laser and this is continuous. There are just two things. So in pulse laser, a 50-second laser is used. In continuous, photo mixing or frequency mixing of two different lasers is used. So there are three different techniques. These are two different methods. Now three different techniques. One is raster scanning, other is time of flight, and one is one-shot imaging. So raster scanning, what you do, you have a terahertz source, means which can generate terahertz. Like similarly, we have X-ray source. Okay, so we can generate terahertz here. Then we expand the beam and fall on this. See here this. Then the sample is moved. Okay, sample is moving like this. Sample is moving like this. You see, sample is moving like this, and you capture pixel by pixel image by controlling the position of the sample, and this pixel by image is captured by either receiver or CMOS camera, CCD camera, or some other detector, and then we capture the terahertz. So this is a pixel by pixel scanning, but the limitation is acquisition time, means that to make the image it takes a long time and the resolution is not so good. So if you see your own old picture, if digital format, you see after some time, if you see now, they are faded. They are faded because the pixel by pixel image capture was not having a good resolution. So when you don't have a good resolution, the image gets fade. Or you see, if sometimes you enlarge your picture, after some portion it sees some dot, you cannot clearly get the idea. So that's why, because of resolution. So resolution is poor. So we need some faster method. So for this faster method, people use camera pixel by pixel image. Okay, so these are the image by this one. Then people try to use terahertz system, terahertz TDS system. Here the same thing, they put the sample here, do the raster scan in X and Y Z direction and capture the image on the detector. Using this, we develop our own system, one shot imaging, and you see the terahertz beam is coming and sample is put here, and this sample is continuously moving. Okay, so image is captured by pixel from here and pass through this lens and optics, and this fall on this zinc telluride detector. And on this zinc telluride detector, then image is passed through this CMOS camera, and from on the CMOS camera we get a 2D image, 2D ST image that we get. Okay, so 2D ST image. So this is same as like color scanner. आपका जो स्कैनर है ना फोटो कॉपी स्कैनर, इज सेम लाइक दैट वन. इट क्रिएट्स ए 2D image by moving the sample. So you see here, point by point pixel are captured. You see point 1, point 2, point 3, point 4, point 5, point 6 point. So like this, on each where the terahertz pulse interact with the sample. Okay, and this is the sample, you see. So beam overlap, beam comes on the sample like this, and it captured the image. And you see, this is the terahertz pulse. In this pulse we captured the image, and I will show you later here. Don't go in this one. So these are the image of Teflon cylinder. This image was captured. You see, there is something here. So these image are captured by this setup. These are the 4 metallic bar inside thermocol. Okay, these are the 4 metallic bars inside thermocol. Okay, so these kind of 2D image we are able to get by this setup. This is our setup, this setup. Okay, so this terahertz setup we use, and we get the image like this. Okay, so this gives us a confidence that terahertz can be used as a image. It can be a new imaging technique. It can be used at many places where imaging is required. And not only imaging, shape imaging. You know, shape imaging is required. Then we did the imaging of some pharmaceutical tablet. You know why pharmaceutical tablet is important? Because when, at the medicine, we must know malfunctional or some other tablet is not mixed with our means peg tablet. So to distinguish and to see, okay, we need the imaging of technique on the conveyor belt. So pharmaceutical industry needs this imaging technique very badly. So then we put the glucose, maltose, lactose, fructose. See, and we did the imaging in just 6 seconds. These are the image of the medical capsule. A clear image will come later. These are the raw data that time. Then we did the image of human tooth. This is the photographic image of a human teeth. But you see, on terahertz, at different frequency, we got the image of this. And you see here, no, we not only got the image, but we see some chemical composition, intracavity inside there is a cavity inside the human tooth. So to know that cavity also, terahertz is a very good tool. From here, if you now do on the Google just terahertz image or imaging, or na, this is the first picture which will come. We started this work in 2013, but this is 2D image. We need 3D image. Okay, so then we have to do computed tomography. Okay, your NMR machine, hana, your X-ray machine you do in the medical image. So they give a 3D image. Okay, so for this we need computed tomography. So computed tomography, the basic techniques are X-ray and ultrasonic. Okay, so in X-ray image, this is X-ray machine. A patient can go from here like this way. Okay, it's a very high penetration power. It can it's advantage that we can see through the bones easily. That's okay. Yeah, but inside you can see through the bones there is some crack or something else, but you cannot see the chemical composition. Disadvantage, it's an inventive effect of ionization, too high penetration which can affect the body, and it gives only monochrome image, not the color image. So it is very difficult to analyze the chemical composition. So then people started terahertz tomography. So these are the image you see, optical photograph of something, and this is the terahertz image of this kind of block. And this is Japanese doll we did that time, and this is the image of this Japanese doll, terahertz image. But this image not good because it needs a long measurement time. So to get a 2D image, some kind of 10 minutes required, 3D image, at least 1 hour is required. A traveler, a passenger cannot wait at the airport for hours to get his baggage to be scanned or image. So how to shorten this one, how to shorten the time? So for this we need high power sources, we need three-dimensional imaging. So to do three-dimensional imaging we need high power sources. So when we go through the high power sources, the most powerful source is accelerator base. Maybe I hope and I believe that you people know accelerator. So accelerator, like here in our RRCAT, BARC, we have accelerator. So accelerator we cannot put on the airport because it gives some harmful effect, operation maintenance, and to run a accelerator there are 5,000 people is required. But a similar power, similar energy can be obtained from a crystal, lithium niobate. So we use the lithium niobate as a source for terahertz. Okay, so don't go in this one. So in lithium niobate, how terahertz is generated? You shine a laser pulse like this on a lithium niobate crystal. This is lithium niobate crystal. You shine a laser light like this, and when you shine the laser light like this, terahertz is generated. Terahertz generated like this way. Okay, so we get a very powerful terahertz source using lithium niobate, and it's the same as like we do supersonic jet is coming out of the sound. Okay, so it's very fast, very fast. Okay, very fast and very high. So then how to do this one? So we use a laser pulse from here, and this is divided by this beam splitter into two parts, and then it passed through this various optics, and this is the lithium niobate crystal. From here terahertz is generated. So this is not easy. If you see my slides, it's very difficult. Okay, doing this is not easy, and this is the reason very few group, hardly 4 to 5 group worldwide are doing. Not in India, only one group. Okay, so if you see, everything must be nicely measured, synchronized. You see, everything nicely adjusted. Skill is required for this kind of work. Okay, so it's not an easy task. If something is mismatched, you will lose the signal. You cannot do the imaging, you cannot do any work. Okay, so this is the typical laser system. We use a regenerative amplifier, and this is my setup where this laser pulse is coming from here. It's passed through this grating and half wave plate, and then from this lens it's fall on this. You see very tiny lithium niobate crystal, just 5 mm by 5 mm by 5 mm, and this accelerator, this crystal can beat the accelerator. So from here this crystal terahertz is generated and is guided by these 4 parabolic mirror, and sample is put here to be imaged. Okay, so we get a very high terahertz pulse of 745 kilovolt per centimeter. You say, sir, what is this 745 kilovolt? You see, the binding energy of a nucleus is just 243 kilovolt per centimeter. It means we can dislocate the nucleus. We can give the instability in nucleus. When it's instability, there are non-linearity. So we can introduce the non-linearity in the system. So by introducing the non-linearity, we can achieve the desired properties. Okay, so this is the comparison. So this is our experimental setup. Like see, you see here. So from lithium niobate, terahertz is generated. This generated terahertz is guided by these two Teflon lenses, and sample is put here. Okay, sample is put here, and then this image pixel by pixel is captured by this zinc telluride crystal. From here, the image gets and pass through this analyzer and again lens and captured by CMOS camera. Okay, and then we get a 2D image. Okay, but we give the rotation to this. Okay, so as I tell you, have you seen the movie? अगर आपने मूवी देखी होगी ना, तो पुराने समय मूवी में क्या चलती थी, रील चलती थी, ऐसे रील, द रील ब्लैक, अगर आपने नेगेटिव देखा हो, रील देखी हो, तो दैट रील वाज 2D इमेज. ओके, एंड दैट रील इज पास थ्रू द लाइट एंड पास थ्रू फास्ट, है ना. तो वो जब फास्ट चलती थी तो हमें पर्दे पे 3D इमेज दिखाई देती थी. ऐसा ही था ना, हमें मूवी में तो
Yes, yes.
हाँ, रील तो 2D थी, लेकिन उसको हम फास्ट मूवमेंट देते, रील ऐसे लाइट के सामने फास्ट चलती थी, और वो घोड़े की एक इमेज, लेकिन खूब सारे घोड़े के एक साथ होती, तो वो घोड़ा दौड़ता हुआ दिखाई देता था हमें, आदमी चलता हुआ दिखाई देता. क्या करते थे, वो जो इमेज थी, जो 2D इमेज की खूब सारी इमेज को एंसेंबल करते थे, एक जगह इकट्ठा करते थे, और फिर उसको मोशन देते थे. तो मोशन हमने यहाँ रोटेशन दिया, और वो 2D इमेज यहाँ आ गई. अब उसका हमने फुल FFT फोरियर ट्रांसफॉर्म किया. फोरियर ट्रांसफॉर्म करने के बाद उसकी जो बैकवर्ड जितनी नॉइस है उसको रिमूव किया गया. फिल्टर बैक प्रोजेक्शन, ये एल्गोरिथम होता है रेडोन ट्रांसफॉर्म, जो एक्सरे में भी इमेज यूज करने के लिए होती है, ड्यूगरोटाइपिकल फोटोग्राफी में भी सेम वो यूज होता है. तो हमने क्या किया कि हमने कोई हाई फाई साइंस के पॉइंट ऑफ व्यू में नहीं किया, हमने हाई फाई टेक्निक के पॉइंट ऑफ व्यू में किया, कि हमने वो जो 2D इमेज जो चलती थी वही 3D इमेज बनाई. अब देखो आप इससे क्या किया, हमने क्या किया, हमने एक इमेज ली, उस इमेज का हमने फोरियर ट्रांसफॉर्म किया, है ना. फोरियर ट्रांसफॉर्म करने के बाद हमें सिनोग्राम मतलब 2D इमेज मिल गई इसकी. अब फिर हमने इसको फिल्टर किया. इमेज को फिल्टर करना जरूरी है, क्योंकि इमेज फिल्टर नहीं होगी तो आपने देखा हो ना, कई बार इमेज पता नहीं चलती है, वही रीजन होता है. फिर उसका हमने इनवर्स फोरियर ट्रांसफॉर्म किया, है ना, इनवर्स फोरियर ट्रांसफॉर्म किया, और इनवर्स फोरियर ट्रांसफॉर्म करने के बाद हमने उसका फिल्टर बैक प्रोजेक्शन एल्गोरिथम से रिकंस्ट्रक्शन किया. तो हम जो पर्दे पे देखते हैं वो रिकंस्ट्रक्टेड इमेज होती है. तो वो सेम कॉन्सेप्ट है जो 2D इमेज का हम रील से लेके चल रहे हैं, वही चीज. ठीक है, ये दिस इज द मैथमेटिक्स एंड थ्योरी. सो वी विल नॉट गो इन दिस वन बिकॉज दिस टॉक इज एट वेरी अंडर ग्रेजुएट लेवल. ओके, सो लेट्स गो. तो हमने क्या किया, उस सिस्टम को लेके आप ये देखिए, हमने 4 थर्म, ये जो हमने है ना यहाँ 4 मेटालिक बार रख दी थर्मोकोल के अंदर. तो अब ये 4 मेटालिक बार थर्मोकोल के अंदर है, आपको आंख से नहीं दिख सकती, है ना. 4 थर्मो, हाँ सर कुछ बोल रहे थे क्या? हेलो.
Hello, hello.
हाँ कुछ बोल रहे थे क्या?
Sir, common language use करिए English ना. I think I request you because most of the students are from South India or not, all over the country.
Okay,
Yeah,
okay.
thank
So
you.
these are the 4 thermocol, 4 metallic bar inside thermocol. Okay, it means we can see in through something is hidden inside thermocol, paper, cardboard. So you see, these are the 4 metallic bar inside thermocol, and by terahertz we can capture. You see, very nice image. This image, I can bet you cannot get such a nice image even using X-ray. So terahertz can be used as a imaging source at airport to check. You can get a very nice image. You see, very nice structural image of a 4 metallic bar inside thermocol. Then we put a toothpick inside plastic. Okay. Our baggage at the airport is mostly inside either cloth or plastic, and we cannot open this one, है ना. So to examine the foreign materials in soft material, you see, now when we did the terahertz image, a toothpick inside plastic can be easily distinguished. You see here. So if you see this one image, a toothpick inside plastic is easily visualized. If you see your baggage, sometimes if you have eyed on the X-ray scanner, the image is just like this one. This is the image of X-ray. You see like this one. But terahertz use a 3D image with clearly distinguish what is inside this one. Okay, you see here, it's give the image what is there. There is a toothpick inside plastic. So it's a very good imaging technique for the safe society. This is the medical capsule. Okay, this is the medical capsule optical photograph, and you see this is the image. Okay, and we see this is upper part here, this is lower part. So drugs is here, drugs matlab medicine. The medicine is inside this medical capsule. So terahertz can give exactly what amount of medicine is there in the whether the capsule is filled or not filled, and to know that we need a very good imaging technique. Okay, and this my paper was selected as a cover page of Optics Express in 2015. It was the cover page. So cover page, you all are researchers, you know the meaning of cover page. Something is breakthrough. Then we did the imaging of a chicken bone. So to show that terahertz can be used as a biomedical imaging technique instead of the X-ray, it can be used there to remove the NMR, to remove the X-ray. So you see, this is the optical photograph we take by camera of a chicken bone, and you see, but terahertz, you see, a pores can be easily seen. Means there is some pores in the bone. Bone is not fully filled, and you see, and this looks shiny, smooth, but it's not smooth. So this can be very good to see our body parts. Okay, to do the imaging of our internal body parts. Okay, and also to see the roughness, to see the smoothness of the body part, which is nowadays replaced by stainless steel, like stent in the heart, and in the joints they use some kind of means stainless steel rods for accident patient and kind of things. So terahertz can be a very good tool to see the internal biomedical imaging, in imaging of the body parts manufactured in the company to fit in the body. Because if the roughness, if there is structure, by naked eye and by other technique, it can seem very smooth, but you see terahertz is not smooth. So these kind of parts, some they will interact with our body and they can make the poison in the body. So to know the accuracy, to know the smoothness, to know the surface roughness of the body part, terahertz is a very good tool. Then this is the Teflon. Teflon is a civil aviation, not only civil aviation material. Most of the part of the plane, rocket are made of Teflon. Okay, so if a small crack is there in Teflon, and other imaging technique is not easily done by this one. And you see this Teflon have a hole here. Teflon have hole here which cannot be seen by naked eye, and it's very smooth. You see, we put this on in terahertz, okay, and the hole is clearly visible using terahertz image. But structure, you see, the smoothness of Teflon is not as we found by naked eye and other technique. Terahertz image gives how Teflon is deformed. You see, it's deformed. If this kind of deformed part is used in plane, it's a fatal to life. It's a risk of the life. 300 passengers are always on the risk. Something may happen. So to check and balance, to remove those kind of fatality, to save the human and money both, terahertz is a very good imaging technique. Then you see, I will tell you interesting part of this. This is the wine cork, okay, and this application came from Dubai. people smuggle diamond inside this wine cork, and this wine cork you buy from duty free shop and come, nobody will check. They get checked before coming to duty free shop. Okay, and people easily smuggle diamond here because x-ray, when you do imaging by x-ray on the glass bottle, okay, light gets scattered, you cannot do imaging. But you see terahertz, it can do a very nice image. You see, just a minute here, you see, uh, this is wine opener, this wine opener is clearly visible here, you see, and this is the image, a wine opener inside. So what is inside this wine cork, it can be easily visualized, you see. So this can be used as a very good imaging technique. Then this is also wine cork, we can check the shape and size. You see here, actual shape and size, something is there or something is not. So this is my demonstration. But now you say, sir, we can do this by X-ray also. Why you need? Okay, so as I told you, there are two other things. One is X-ray is invasive, ultrasonic is contact. Terahertz is non-invasive, non-contact. First thing. Second thing is that one, by terahertz, we know the chemical composition. So this is called 4D imaging. Okay, so have you seen 4D movie? Anybody? So you see, the movie is 2D, the movie is 2D, the reel is 2D. When it gives a fast movement, you see a 3D movie on the screen. But in 4D movie, if a horse is running, you feel that you are riding on the horse. It gives you an extra feeling. Okay, that extra added feature. Okay, then because when there is a rain, okay, you feel a shower because from up they will put some kind of shower on you, so you feel rain. Okay, you are feeling by yourself. Okay, when horse is riding, you are feeling that your chair gives you feeling that you are riding on the horse. So that feature is added in your chair. Okay, so similarly, what kind of material it is with the image. So if we do image of this one, and these are two different medicines, one is lactose, one is sulfagitol. If we distinguish with this image, okay, then we can call it 4D image, and that's why it is very good. At the airport, if somebody take liquid explosive, somebody take RDX, somebody take any other component, medicine, it can exactly tell what medicine it is, what drug it is, what explosive it is. Similarly, we did the experiment with or sulfagitol lactose, and then two other medicine. One is histidine, and one is also lactose. So they turn white. They clearly distinguish. So terahertz can be used to distinguish between medicine, between drugs, between explosives. And we can do 5D imaging, 3D image with fingerprint spectrum and concentration. So we know the exact thickness of the medicine tablet, because thickness of the tablet is very important for crucial life-saving drugs. Okay, if thickness is more than the limited amount in micron, it's a fatal to life. There is a fear of means something bad happened to the patient. You see, so now terahertz is used to do the imaging of medicine. You know, these are the, so you don't think that medicine come directly to you, company packed like this. No, company will do all the other things before packing into. That's why there was never a single medicine in let's say you buy the paracetamol, then all the 10 tablets are paracetamol, not a single tablet is different. So they scrutinize like this before coming to you in the market. Okay, so then now this work I am doing jointly with Korea Atomic Energy Research Institute, and many people ask me, is there some harmful effect of terahertz on the body? So this is at initial stage. So we made the terahertz system like this. Okay, you can see this is tera radiation setup. The beam is coming from FEL accelerator. Okay, and this is my setup cavity. So we put a anesthesia mouse here. Okay, this. Okay, so on one we put the terahertz, and one chamber we don't put any beam. Okay, and we check. Okay, so there are two holes, you see. One passed by terahertz, another is just without terahertz. Okay, so with this anesthesia mouse we check, and this is the camera, terahertz camera. Okay, and this is terahertz beam. And by this we did at the very different places of the body part, not only the ear or something like that. Okay, so this is mouse, and this is this one. So we found, you see, non-irradiated and irradiated, there is a just change of 0.02 degree, means it's have no harmful effect on the body, no harmful effect. So this kind of setup is needed terahertz. You see, this is the airport security conveyor belt. You check the baggage like this, and the person, CISF person, check the image here, and on this basis he check your baggage. So terahertz can be used for medical, airport, and homeland security in the metro, bus, offices, anywhere you can put, hotels. Okay, so this is the terahertz image. You see, this person kept carry the knife. Okay, by X-ray you cannot see, but by terahertz you can see. See here, he captured carrying the knife. This man take the gun inside his body. This is the terahertz easily can see. By X-ray and other things you cannot see. So it's very good security tool. Okay, this is chemical. Somebody send three different drugs inside this envelope. You cannot find. But by terahertz, you know, this is MDMA, this is aspirin, this is amphetamine. Okay, and this was the clear case of imaging at the post office security. That some drugs is not transport in your mail or in your Amazon and Flipkart boxes. So terahertz can check that one. Explosive, terahertz can easily distinguish the explosives. And you see explosive detection in your FedEx card. That time FedEx was so popular, so people use FedEx. Now Amazon and Flipkart also there. VIP security, if somebody have gun inside his cloth, how you can check? You cannot touch the VIP. Okay, if you touch the minister, they will get angry, and then it's no way. And that person, VIP person, is himself carrying some kind of gun or some kind of knife. How can you check? You can check by terahertz. A person is checking. You see this gun, it looks like gun. You see here, hidden weapon inside the body. You can check the gold and silver inside, people keep inside body. Very highly drugs, people solo inside the body and sit in the airplane, then go and then vomit and take out that one, and they do kind of illegal services. Terahertz can check. This is explosive detect. He is my friend. He came to my laboratory and he made terahertz explosive camera to detect explosive. Because now, you know, 100 ml, you cannot take more than 100 ml. So people believe that up below 100 ml, if there is some liquid explosion, it will not give some kind of fatal explosion. But now by terahertz, you can check. You can see a man through the wall. There is some man through the wall. You see a man. So terahertz can be used to image. If you send drone, people will know, okay, because there is voice or something like camera. Okay, so if a militant, if a terrorist is hiding behind a wall, or capturing suppose women or children and hiding behind the children, how can you see? You cannot see. Terahertz can see. Okay, what is inside this box? Whether cup is filled or half filled. So terahertz can see. No need to take off your shoes. If you know, if you have to take off your shoes at the airport always, most of the time, if you go international flight, because we cannot easily see through your shoes. So they have to put in the X-ray machine and see. But now no need to take off your shoes. Okay, imaging can be easily done. destructive testing means cracks, defect you can see. You can do the quality control. You you can see the water content by imaging. Okay, so this is very good for agriculture. So grapes at some certain water content to be the harvested. If that is more than this one, that water content, they will definitely get rotten and hold the crop will kind of things. So there are many crops which needs to harvest before exact water content. When to harvest? Biomedical imaging, you can distinguish between cancerous and non-cancerous tissue. Okay, tumor detection, breast tissue, you can easily see where is the tumor. You see, in X-ray image, you cannot see anything. This is the X-ray image of breast, but by terahertz, you see this is tumorous, this is non-tumorous. Okay, this is optical tweezer. Let's show. You can distinguish between fake and genuine currency. नकली नोटों को निकाल सकते. You can distinguish between fake and genuine currency. You can see inside what is written, what is there in the mailbox, what it is written. You see, so you can see, you can read without opening an envelope. For high-fi securities letters, you cannot open. You can, which are security breach, you can see what is inside. In 1986 or in 1981, when Indira Gandhi ordered that if you find a suspicious mail, you can open and read it. But then the President Gyani Jail Singh told, no, it's a breach of personal freedom writing. Okay, so we cannot do that kind of things. But with some kind of national security threats, we can see by terahertz what is it written in the mail. An application in arts, you cannot remove the old 5,000 paintings and touch or something. But what kind of painting? Terahertz can give a clear picture what is kind of painting it is. It can see, because terahertz can pass through the soil. Okay, so it can be used for conservation of art. It can be used for disaster management. It can be used to locate a body beneath under the soil. Like in Uttarakhand, there was kind of flood and some building is supposed fallen, some bodies down the building. There was no technique to locate, identify where is body, until unless we just means remove the garbage and all kind of malba and other things, and then we see the body. But terahertz can see. Let's don't go. Anna, this medicine, food chocolate, this also done when I was in Kyoto in my lab. So food inspection, sorry. Okay, so there is glass, metal and stone. Okay, so what is there? You see here this in chocolate. So coming year will be the golden year. So I will say terahertz is Aladdin ka chirag. Aladdin ka chirag. We can do a magic. We can know the image. With this, I will finish. So terahertz is very useful for our life. Okay, with this, I finish my talk. I hope.
Thank you very much, sir. Thank you very
Thank
much.
you very much. I hope you understand.
Yeah, of course. Now I invite a question from the student as well from the faculty members.
So, how far can terahertz detect something?
Oh
How far?
yeah, yes, very good. So people have went up to 200 meter. 500 meter also demonstrated, but 200 meter is commercialized. Standoff detection is up to 200 meter. So up to 200 meters, you see the body is below just 2 to 5 meter for disaster site.
Sir, is there also a way to hide from terahertz? Because you showed a man from a wall also.
Yeah, yeah, man. Yeah, so you can see through the wall. You just need a high power source.
So, but this is a privacy issue, a security issue. How can we prevent that from happening?
Yes, yes, yes. Yes, by terahertz we can see and prevent these kind of things, because most of the cases, not only that means a suspicious person can hide behind the wall, behind the women, children. In that kind of case, you can exactly locate and then destroy the target, and that is already in use now. There is terahertz radar also. That is already in the process. US
Sir,
has
I am asking how can we hide from terahertz?
we cannot hide. We can hide only by metal wall.
Okay, sir.
Metal wall. You got my point. Terahertz cannot pass through the metal.
Sir,
Hmm.
why water is not allowed to carry in the airport?
What? Why?
Water bottle.
Water bottle. Because people suspect of liquid explosive.
So it means it does not able. It means this terahertz is not able to
Yes.
detect
No,
this.
no. Terahertz is now. I showed the liquid explosive that PPT maybe you have not seen.
Yes,
My
yes.
German friend, they made the explosive, Terra detector liquid explosive. But it's terahertz birth is in 2009. This
Okay,
is
okay.
not fully mature technology yet. Someday it will be, but at this
It
moment it's
means
not commercialized. It's on the demonstration level now.
it means the high frequency is required for detect the water molecules.
No,
The people.
actually, no, no. If you have broadband source, so water
Okay.
absorption peak is around 1.2 and 1.6 terahertz. So if you do imaging or other things below, other than these two frequency, you can detect.
Okay.
Hmm.
Yeah. Any questions?
So,
Yes,
what
I
is
have a question.
Hmm.
Go ahead.
My question, it's a very interesting talk, and it was, you're showing that this technology is much more capable than X-rays. But
Hmm.
how expensive is this technology?
Sir, at this moment, of course, initially when you buy a phone, also it was very expensive. But now you see, not so expensive. So now it's of course expensive because we don't have terahertz emitter, detector, fully mature kind of things. People are just making it. It's okay. So if this at this moment, if we want to make a terahertz scanner full system, we need at least 6 to 7 crore. But X-ray is 20 lakh. So that's the reason. And in most of the airport of the world, there is now terahertz scanner, no X-ray. Only our India and few underdeveloped countries which cannot afford, they are only using the X-ray. If you go US, you go Europe, all are terahertz. So it's of course at now it's expensive.
so what is terahertz time domain spectroscopy?
Correct. Yeah, man. Time domain spectroscopy not so expensive. It may be in 1 or 2 crore. Only the main expense for such kind of technology is laser and especially high power laser. Laser and crystals are very expensive. Yeah, if this talk will be offline, then it will be more interactive there.
Yes, yes.
Uh, I have one simple question
Hmm.
that what is the effect, biological effect on particularly human being?
Sir,
Is
I
there
saw I showed you the slide of mouse if you remember.
I might have missed that
Yeah.
slide.
Yeah, so we check using very high power FEL, free electron laser, accelerator base on mouse, because crystal also not so high powerful. So we use the FEL I was in Korea Atomic Energy Research Institute to do this experiment, and we found no harmful effect till now.
Okay,
So
okay.
that's the reason terahertz is in communication now also, because there is no harmful effect. And if you know now, if all of you, I will tell you one thing: 6G communication is only possible by terahertz. 6G communication can be only done by terahertz. So this is that one is the its bandwidth, high terabit. Now we are using 20 gigabit per second or to maximum 100 gigabit per second. Of course, at the home we have just 100 Mbps, but by terahertz you use 1 terabits, very fast. And second thing is it's no environmental hazardous effect like tower ka radiation, the other things will not be there.
Thank you.
Uh, uh, Hello, sir.
Hmm.
Actually, some of our students are interested in internship and agitations. And what are the facility and criteria of feasibility at the
See the
institutes?
this one. Yeah, we have laser. You see, I'm in laboratory now, so you can come anytime and see. At present, how to use terahertz to make $1 billion market. Of course, if we fully commercialize and demonstrate this technology, it's $1 billion market. So in the my last slide, I have said terahertz. The coming year will be golden year of terahertz, and coming era is tera era. Now you saw at present is laser era. Everything is done by laser. Whether it's defense, whether it's astro, whether it's medical, whether it's a transport, whether it's a measurement. Everything is done by laser. Coming days will be for terahertz. You want to actually I'm in a process to buy the instrument, this kind of instrument now. So you can come and see after maybe 5 or 6 months. Any other question?
Okay, let us thanks to the speaker.
Thank you very much.
I invite Dr. Professor Ashok sir and give a vote of thanks to our speaker.
Thank you, Jagjeevan. Uh, Thank you, Dr. Guruvendra. It was
This is
nice
Dr.
talk.
Mukesh,
Mukesh. Dr.
Mukesh.
Mukesh, okay.
I'm
I'm
sorry.
from my
Uh-huh.
student's PC.
Acha, acha,
Okay.
acha. I'm sorry. Dr. Mukesh, I am sorry.
No
So
problem.
it was a nice talk, and I think students must have enjoyed a lot, and especially they must have got fascinated in the sense that it has a lot of practical applications. It is our experience as a teacher also that whenever a student see the application aspect and the day-to-day life applications of any technology or anything, so they get more fascinated and get attracted. So thank you very much, and the way you presented with the common examples, so it benefited a lot of students, including the teachers. I also got. I'm sorry in the very beginning because of some reason I could join little late, so that could be the reason I missed a few slides.
No
So
problem.
again, thank you very much, and I, on behalf of the physics department, all faculty members, IQAC, and the college, thank you very much for sparing your valuable time, and you benefited our students, and I hope that Dr. Jagjeevan would be in contact with you, and we will have a better another speech by you for our students. Thank you again, Dr. Mukesh. Thank you
Thank
very
you.
much.
Thank you, sir. Thank you very much.
Welcome.
Thank you very
Okay.
much, Mukesh ji. Thank you, sir. Ashok ji.
Thank you. Thank you.
Thank you, Mukesh ji.
Thank you,
Uh,
sir. Thank
was
you.
really a very interesting and stimulating talk. Thank you very much, sir. Thank you.
Thank you. Thank
Bye,
you.
sir.